And then I will give the floor to the last speaker, Timm Oertel. Please go ahead and share your screen.
Okay, thank you very much. Everything fine? You can hear me and see my slides? Okay, fantastic. So I want to talk on the support of lattice elements and semigroups in this talk. And this is joint work with Iskander Aliyev, Gennady Avakov, and Jesus de Loera. And the setting I am in is actually quite simple. I'm just looking at solutions of linear systems of equations. And just to make the setting clear, I assume that my matrix A is just an integer matrix, and that my right-hand side is also just an integer vector. And then I just want to impose the one additional assumption that if I look at all the minors of my matrix A, I want to assume that their GCD is simply equal to 1. This is actually not a big assumption. It just makes my life easier and maybe also your life a little bit, but it's not a big setting. So when we look at these systems of linear equations, I think there are like 4 very classical settings and theories for solving these settings. So probably the very first one comes across is just when we assume that we want to solve these kind of systems of equations over the reals. And this is essentially just the theory of linear algebra, very classical. And a little bit more complicated already is if we actually want to solve these systems over the non-negative reals. In this setting, we actually come to the theory of linear optimization. But now, in order to actually give some credit to the I and the P of our IPCO conference, the more interesting settings that I want to talk about is what happens actually when we ask for solutions where X is an integer vector. That's then just like solving Diophantine systems of equations. And last but not least, what happens if we ask actually for a non-negative integer solution? So what is if we're in the setting of linear integer optimization? Okay, so these are kind of the 4 settings. And the question I want to look at here today is whether we can actually find solutions, X star, let's say, that have small support. So solutions that have as many zeros as possible. I don't know if this needs motivation, but I can give it a try. So like these problems of minimizing the support for solutions of linear systems comes up in compressed sensing or the correction of errors in like codes. It has also been used to construct like approximation schemes and so on and so forth. But I think in its own, it's already like a very justified question. I mean, everybody who likes it neat and tidy, I mean, will agree that having loads of zeros is most likely to be a little less messy than having like some solution with lots of different values inside. Okay, so this I think should be enough for the motivation. So what can we actually say? So if we actually really try to minimize the function, like the support function, over, for example, the reals, it is already well known that this problem is already NP hard. But if we kind of put the B aside and look more at the parametric version, like AX equals B for all B, what can we say in that setting? And there from linear algebra, we actually know immediately that we can always find a solution where the support is equal to the rank of the matrix A. And given our assumption that the GCD is actually equal to 1, this indirectly implies actually that the rank is simply M. So we can say that if we want to solve the system of equations over the reals, we can always find one with M. And very similar, or like an extension of this, if we ask good old Kara-Theodori, he will actually say that even if we are looking for a solution over the positive, like the non-negative reals, then we can always find also a solution with at most M elements. So this setting is actually very well understood and everything is known. So what I want to concentrate on in this talk is actually the 2 other settings. And I want to ideally find parallel or like equivalent results to these 2. So if we look at the setting where we tried to actually solve the Diophantine system of equations, we know quite easily that there is a solution if and only if the right-hand side B is actually an element in the lattice generated by the columns of A. And by our assumption that actually the GCD of all the minors is equal to 1, this is actually nothing else than just having the assumption that this lattice spanned by the columns of A is just equal to the standard lattice in n dimensions. And the value that I want to actually now bound, like in relevance like to the classical rank, is what we call the integer linear rank of A. And that is just looking at all elements of the lattice Zm, and then always looking at the minimum support in order to express this element in terms of the columns of A with as few columns as possible. So it's like this max-min problem. And if you like, you can look at it like this. So assume that we're just given a certain lattice, lambda, by some generators, and we just want to look what is like the worst case of generators that we need to express a certain element of this lattice. And I mean, this is like a little bit different, of course, than having a basis of the lattice. So we just look at generators. And very similar to the integer linear rank, I also want to study the integer Carathéodory rank of A. And that is just the same as above, just with additional positivity constraints. And in this talk, I want to give two, in my opinion, quite nice bounds for both of these ranks. The first one is of very algebraic nature, and the second one uses some more geometry arguments. And then in the very end, I'll just want to mention like a few comments I'll give a few comments on complexity questions. So I hope that the setting is clear. I'll also go a little bit into the detail on what there is on the like in the literature on the integer Carathéodory rank, but very surprisingly, we didn't actually find anything on the linear rank. Maybe we're just bad in searching, I don't know, but yeah, there was definitely some kind of gap. So I'll start with the integer linear rank. And for that, I would like to introduce some notation. So if we have a natural number Z, we know that just by standard number theory, there exists a corresponding unique prime factorization. And given this factorization, we can define the so-called prime omega function. And the omega function itself just counts the number of prime factors. So this is the first omega of Z. And then we can also define like a variation of this. This is the so-called truncated prime omega function, which just counts the number of prime factors, but we cap everything by an m. And then if we just set m equals to 1, this is the little omega function. This just counts the number of distinct prime factors of Z. And just to give roughly the order of these values, I mean, clearly the omega function is always less or equal than the logarithm with a basis of 2. And then repeatedly, the truncated omega function is smaller and the little omega function is even smaller. And just to give like also a little bit like a rough idea on the size. So if we look at the average size of like the omega Z function, this is actually not even close to this log of basis 2, but it's more of the order log of Z. So it's a lot smaller than log of Z. And with this notation, we can actually give right away the main theorem for the integer linear rank. And that states that if we have any element in our lattice Zm, then we can always find an integer solution, x star, such that x star is equal to b, and the support of x star is less or equal than m plus the minimum over all possible minors from A and the corresponding truncated omega value of that. I mean, maybe I can also just say right away that, I mean, there's actually no hope to find anything that only depends on m, like in a similar way as in the real setting, because I mean, otherwise all of us would need to look for new research field. So it is kind of expected that we need something like the entries of A entering any kind of bound that we want to give. Okay, proving this uses some arguments from algebra. If we want to prove this theorem with the omega, the truncated omega function, it's actually a little bit more work, but I think I can quite nicely motivate the main ideas by just proving the statement for the omega function. So if we just forget about the m. And for that, we actually prove something slightly different. So again, as above, I just want to denote lambda of A just as the lattice spanned of A. And now I'm just going to fix a subset of m, like n elements from 1 to n. And I'm assuming that the corresponding minor A of tau is just non-zero, so it's non-trivial. And what I now claim is that there exists a superset of tau and a subset of the indices 1 to n, such that actually the lattice of A is equal to the lattice of A gamma, where gamma is just the matrix with columns I, where I is in the set gamma. And I want to assume that this, and I want to prove that the cardinality of this set gamma is actually less or equal than m plus omega of the determinant of A of tau. And if this is true, of course, also the statement would be true for the smallest possible choice of A of tau. So I think that's clear. Yes. Obviously, this is a slightly different statement than what we were proving, what we want to prove. So this is not quite the integer linear rank, but it's actually, depending on the point of view, a slightly stronger argument. But proving this actually then goes quite nicely. So what we can now define is just the quotient group lambda of A over lambda of A of tau. And the number of group elements in this set is precisely equal to the number of the determinant of the lattice A of tau, which, since A of tau is a square matrix, would be just the determinant of A of tau. So let's assume that these big black dots define somehow our A of tau. Now, if we assume that this lattice lambda of A of tau does not span Zm, then we know that there must exist some I such that the ith column of A is not in this lattice spanned by A of tau. So what we can now do is we can just define the set gamma as tau union with this element I, and look at this new quotient group lambda of A over lambda of A of gamma. And what we have is that this new group G of gamma is a strict subgroup of G of tau. So first of all, it's again, the cardinality must be an integer, and the integer must be a divisor of the cardinality of G of tau. So it is strictly, so if we look now at the gamma function, we know that it's strictly less than the omega function. It is strictly less than the original omega function. So we have decreased it by at least throwing out one prime factor, the prime factorization of the initial prime factorization of the determinant of A of tau. And now we could just repeat this argument, and after at most omega of the determinant of A of tau many steps, we would have to have that we have a group with only one element, and that would then correspond to actually having found a basis for lambda A, which is nothing else than Zm, the standard lattice in m dimensions. And that actually already proves this slightly weaker statement where we just use the omega function. I hope this is clear. So maybe just a few remarks to this theorem. I mean, we can actually find in a certain way for always examples where the value of the theorem is actually always obtained. So it is optimal in a certain sense. And then, as you've seen, the theorem is actually constructive. So if we are not necessarily like minimizing over all these possible choices of tau, but just like fix a set tau, then we can actually also find a sparse solution in polynomial time. So it's actually also gives rise to a polynomial time algorithm to find a relatively sparse solution. Not necessarily the sparsest, but a relatively sparse solution. And actually also the way how we actually got initially to this problem was we were actually looking at the semigroup setting. And actually this gives rise immediately also to a nice corollary that gives a bound for the semigroup setting. So again, if we have a positive integer Zm, it should be also stated that it's like has a feasible solution. Then there exists actually, and if we assume that actually the cone of A spans positively R of M, so if we just look at the cone of A, it's equal to Rm, then we can guarantee that we always find a positive integer solution such that A times X star is equal to B, and the support is essentially of similar size as in the other setting. Only difference is that we have now 2m plus this minimization omega term. This follows quite easily. But in a way, having this assumption that the cone of A actually spans Rm, we artificially kind of bring ourselves into the initial setting. So the question is actually, can we say anything else if we are like in slightly less like linear settings? And there are actually several results on that. And maybe I'll just point out briefly which I am aware of, like some of them which I'm aware of. One of the very nice settings is when the matrix A actually forms a Hilbert basis. So that is, if the semigroup, essentially, if the semigroups defined by A, so all positive integer combinations of A actually relate to all integer points in a cone, then A is actually called to be more or less a Hilbert basis. And in this setting, there are actually bounds that are independent on the entries of A. And one can actually show that there always exists a feasible solution X star with support less or equal than 2m minus 2. And 2m minus 1 was initially proven by Cook, Fundlup, and Schreiber, which then was later improved by Chabot by 1 value. And maybe also just briefly mention that initially the thought was that actually the Kara-Teodori property might hold, so that actually you can always find m elements, but there has been actually an example has been found where you can show that you need at least 7/6 times m many elements to generate a certain element in this semigroup. So the initial conjecture was false. And the precise bound is actually still open, which is also a very exciting open question. If we want to go a little bit more general and not necessarily have this Hilbert basis property, 2017, Aliyev et al. Were able to prove that you can always find solutions with support at most 1 plus the logarithm of the maximum entry of then the column of A. And even more general, like for general M, there was the first result by Eisenbrand and Schmoyen, and they showed that you can bound this, so like the support of X by 2m roughly times the logarithm of the maximum entry. And also again with colleagues, we were able to actually improve this a little bit and show that you can always find a solution that is less or equal than m plus the logarithm of the determinant, the square root of the determinant of A times A transposed. And the nice thing here is actually that this under certain unimodular transformation is actually invariant under, while, I mean, if you apply certain unimodular matrices on the Eisenbrand and Schmoyen results, you can actually make this A artificially large. But I mean, just in order to compare them a little bit, of course, you can always write the determinant in terms of the maximum entry. And then we can actually show that essentially we're able to reduce this m factor in the logarithm to a square root of m, but that it's essentially a minor improvement. And maybe also at this point, I mean, there was like another follow-up paper where we showed that we can actually even go one step further. And then even if we now try to maximize or minimize some linear function over like all the possible solutions to a system of equations. So if we're in the classical IP situation, we can actually also find an optimal solution that fulfills this bound, because in this proof, there was actually a certain degree of freedom that we haven't used. And what I want to show today is that we can actually also use this degree of freedom to actually decrease this support bound. And for that, I mean, we can write this determinant also in terms of like with the Cauchy-Binet formula as the sum of all these minors. And what we can do is under certain assumptions, shave off a fraction of m over n summons of this setting. And what we can show is that if we have again our matrix A and we assume that the cone spanned by the columns of A is actually a pointed cone, and if we assume that A1 is an extreme ray of this cone, then we can always find a solution where the support is at most m plus, again, this Cauchy-Binet expression. But here now we always assume that in all these gamma sets, we always assume that the first index 1 is also an element in this gamma set.
Okay, you have 4 minutes, Tim, okay?
Okay, so this setting becomes even more like a little easier and nicer if we look at the setting where m is equal to 1. Then the pointed cone assumption just relates to saying that either all elements a1 to an are positive or all are negative. And then let's assume that they're all positive for the moment. And then the extreme ray are just either the smallest or the largest entries. And then what we actually get is that we can just take the smaller one of the two extreme rays, and we can say that actually we always find a support, like a solution where the support is actually less or equal than 1 plus the logarithm of the smallest entry. So this is an improvement to what we had initially, say that the logarithm of the largest entry. So this can also be a significant improvement. At its core, there is like a nice application of Minkowski, and I think it is easiest to show this actually on the for the one-dimensional setting, for the knapsack setting, where we just have m equals 1. And I at least want to give you with this like the main idea of the proof. And what we can actually show is that if, assuming that we have a solution where there are too many non-zero elements, we can actually find a direction where we can perturb the solution to without becoming infeasible. And that's essentially the statement of this lemma. I don't know, for the sake of time, I'll try to make it short. So assume that we have actually this minimum support solution, and we assume that, let's say, the first T elements are all positive. Then we can just use this upper lemma to actually perturb our solution and find a smaller solution getting a contradiction. And behind this lemma, there's a simple argument of Minkowski. And the idea is just to define the right, I mean, as it's usually always the same, we have to find and define the right kind of set, the convex set. And here it is essentially just this skewed cube that we can write as this, or alternatively, we can also write this in terms of linear mapping M and the infinity norm. And then what we see is that this volume of this set Q is, with our assumption, just strictly greater than T, which always then implies that we can apply Minkowski's first theorem, find a non-zero integer solution, and then by construction of the set Q, all the entries I equals 2 to T are all plus minus 1 or 0. And then by symmetry, we can also just enforce the first variable to be a positive element. So this proves this lemma, and with that, then also the corollary. And just to use the last few minutes, I just want to mention a few things about the complexity. So recall that the definition of the ICR what we can actually show here is that computing the ICR of A is actually strongly NP-hard. If we fix M, then computing the ICR is actually NP-hard. And if N is fixed, then we can actually show that computing the ICR we can do actually in polynomial time. This is based on, the first two things are reductions to covering problems. And the third point uses essentially Pressburger arithmetic. And just to actually finish the talk with an open question. So what we haven't been able to determine yet is if M is fixed, is it actually still strongly NP-hard? So fixing M, let's start with the easiest setting where M is equal to 1. So assume that A is just like a single column. In this setting, is it still strongly NP-hard to compute the ICR? The same thing you can also do with the integer linear rank. Everything should be equivalent. But this is like a nice open question, with which I would like to finish my talk. Thank you.
Thank you very much. I'll see if we have any questions. If you have questions, it's easiest if you raise your hand. Yes, I have Andreas Scheber. Please, you can unmute yourself and ask a question.
I see. Your last question, your very last question, looks very much like a question on empty simplices. Oh, yeah.
Andreas, I don't know what is going on with your sound, but you have a very...
You don't hear me?
Very poorly.
Okay. Now?
It's a lot of strange noise on your microphone.
I try to, it takes time, then I will write an email because it's a bit, I don't type quickly enough, so I think I tried one more thing. I don't know, yesterday it worked very well. It's a good lesson for tomorrow when I will be a chair, then
Try turn down your audio.
Pardon?
Your volume is maybe too high.
Can you use your headphones?
Yeah, but it takes time until it's...
Okay.
Well, let's leave it by email to... I don't know questions and others toward at the end of the session. At the end, maybe if there is time, then I will try to install my headphone.
Okay, can you mute yourself then again? I don't know if we have any other... I don't see any other raise. Oh, Joe, you have a question. Please go ahead.
Yeah. Thanks, Tim. Nice talk. So here you explore a few different parameters that affect this sparsity question, right? So like the determinant it measures how large these simplices can be. And you also talked a little bit about these other parameters that go into the structure of the integer points in these simplices. Are there other parameters that dictate the structure of these semigroups that might be helpful?
Do you hear me now?
Not that we're aware of.
Pardon?
Okay.
Is it good? Okay, so...
Andreas, just hang on a second, because Joe Pat is in the middle of...
Oh, sorry, I didn't realize.
Okay.
No, at the end. Okay, sorry.
I'll give you the word when
Yeah.
Joe is playing. Yeah.
Are there other parameters that are considered in the literature for understanding the structure of these groups? That you're aware of?
That I'm aware of. In the end, you want to have some kind of invariant properties. Like, the determinant is a natural one, because if you apply unimodular transformations, things shouldn't change if the problem doesn't change. And yeah, in many settings.
That's right. So, but if you have a determinant of 4 or 8, then these integer points, these residue classes could all live on a line. And this would be sort of a very nice case, right? Where you only have one generator.
But this then depends a lot more on the matrix A. I mean, of course, you can find loads of examples where our bounds are not tight, but then on the other hand, for every integer k, you can construct the matrix A such that the minimum subdeterminant, like non-trivial subdeterminant, is equal to k, and has precisely this bound.
But you're not aware of how to use this additional structure. If you have more insight on
no, I'm not aware of how to.
Okay, thanks.
Okay, Andreas, you can ask your question now.
Okay, thank you. So in your very last question about Kara-Theodori for just one integer vector, it looks very much like the question on empty simplices and lattice-free simplices, which is lattice-free in another sense, not in the same sense as Joe defined it, a slightly different sense. So you have integer vertices, you have integer vertices, and you take their convex hull, and you call the simplex integer empty if there is no integer point at all in the convex hull, not even on the faces. And the status, as far as I know, the status of this problem, whether to decide whether a simplex is empty is still open, and it is still open in the case when there is only one integer. No. If there is one, this one is evident when there is only one integer vector and the others are unit vectors. Anyway, I don't know whether it's related to any of your techniques new techniques that you have to decide whether an integer simplex is empty or not. So maybe it's a question in this form to Joe as well. So is simplex lattice free? Is this problem polynomially solvable or NP hard?
I mean, like our motivation of this was a little bit more from the point of view that there's like all these parallels to integer programming that you can actually do like these dynamic programming strategies to solve actually knapsack problems. And I mean, it boils down simply to the question whether you can do something similar, maybe also to the integer Kara-Theodori rank or not. But I haven't thought about the lattice-free sets. I'll have to look into that. Thanks.
Okay, thank you very much. I suggest that we take possibly remaining questions over to the Slack room, and that we close the session now. But before we do that, I would like to invite everyone to unmute themselves and give all the speakers in this session a good round of applause.